Hello, my name's Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering. And in this lecture, I'm going to talk about processor caching. And caching is basically the addition of an area of high-speed memory very close to the sort of main core of the processor. And it's meant to help with one of the fundamental bottlenecks that we have to face when designing computers, and that is caused by the fact that memory is typically much slower than the actual sort of ALU type calculations that we do within our processor. So typically, our ALU can execute one instruction per clock cycle. And so, for example, the ARM Cortex-A57 has a clock speed of 2 gigahertz. And so that means we can perform a calculation every 0.5 nanoseconds, which is pretty quick. However, memory access, reading and writing from memory, is always much slower than the ALU. And even if we look at memory in general, not all memory is created equal. And so let's take a look at some memory examples. Let's start off with what most people think of when we say the memory of a computer, and that's double data rate DDR dynamic RAM, or DRAM. And so for those of you who have built computers before, this is the RAM that you buy to sort of plug into your motherboard. At time of recording, DDR4 3200 memory costs approximately $7 per gigabyte. And the 3200 means that the memory has a maximum bandwidth or data rate of 3200 megabytes per second. And this is basically the rate at which you can pull bytes off of the memory or write them to the memory. And you achieve this maximum data rate only if you're clipping through sort of consecutive addresses. So if you are pulling bytes out of addresses that follow one after the other in memory. You tend to do a lot worse if you're hopping around a bunch of different addresses. So for a 64-bit processor, when we do achieve the 3200 megabytes per second, this means we get one word every 1.25 nanoseconds. And it's not too bad. Like if we think again back to our ALU of doing one calculation per half a nanosecond, then it looks like we're somewhere between 2 and 3 clock cycles to get a word out of main memory. However, like I said, this gets quite a bit worse if we start hopping around different sort of disjoint addresses. And this is where the latency or access time parameter of memory comes into play. And so the latency is basically how long it takes to access a discontinuous regions of memory. So if you have an address, way down, like an address that's all zeros, for example, and then you want to jump up to an address that's all ones, those obviously aren't consecutive addresses. And when you make a big change in the address that you're trying to access, all of a sudden your access time jumps from 1.25 nanoseconds for about 10 to 50 nanoseconds for DRAM. And this means that assuming a 2 gigahertz clock rate for our processor, all of a sudden memory accesses are taking many multiples of a clock cycle. So 10 nanoseconds would be 20 clock cycles all of a sudden. So that's kind of the ballpark where we're at. We sort of assume that main memory access takes somewhere between 20 to 50 CPU clock cycles, whereas an instruction only takes one, right? So now you can start to see why memory is such a bottleneck. So can we do better than DRAM? We can. So static RAM, which is a different design of random access memory, or SRAM, is quite a bit faster than DRAM. It is, however, quite a bit more expensive. So, and it's a little bit, like if you go online, it's a little bit of a challenge to get good specifications for SRAM, because SRAM tends to be built right into the processor chip itself. You don't buy sort of like separate SRAM chips that you plug into a motherboard, for example. And but if you look at various online sources, rather than costing $7 per gigabyte, SRAM is around the $5,000 per gigabyte range. So way more expensive than DRAM, many orders of magnitude. But it's also very fast. And there's a little bit of a spelling mistake there. Its latency is approximately a half a nanosecond, which is more than twice as fast as DRAM. And so all of a sudden latency is sort of getting on the order of a single clock cycle. So we can approximately read and write from SRAM as fast as we can perform our calculations. And as a result of its speed, but also its cost, we tend to have a small amount of SRAM in our computers, and we build them right into the processor chips themselves. And so we have this sort of high-speed staging area of SRAM that we refer to as a cache. And the whole purpose of this lecture is to understand how caches work, basically. Going in the other direction, if we want to get slower, of course, when we think about a computer, we've got our RAM, random access memory, and that's where we kind of store temporary information, but it is volatile storage. So when we turn off our computer and turn it back on again, anything stored in RAM will have disappeared. In contrast to that, we also have non-volatile storage, and non-volatile storage promises to continue to store its data even if we turn off the power and then turn it back on again at some other time. And a very important form of non-volatile storage these days is flash memory. And flash memory is quite a bit cheaper than RAM. It's only $150 per terabyte. And we see flash memory used, in USB memory keys, but also increasingly in what are known as solid-state drives or solid-state hard drives, which are computer hard drives that we plug into our laptops and our desktop computers that are used in place of magnetic hard drives. And flash is big, it's cheap, but it's also very slow. It's much slower even than DRAM. So the memory latency is tens of microseconds rather than tens of nanoseconds. And the speed or the bandwidth of most solid state drives today is in the range of 3,000 to 4,000 megabytes per second. So if we compare that to DRAM, it's kind of same order of magnitude, right? But again, this is for sequential reads and writes. So if we're just reading, consecutive adjacent words out of memory in a big chunk, we can get these maximum bandwidths. If we start hopping around different addresses, as is common when we read from a drive, then all of a sudden the latency really starts to hurt us, and then this tens of microseconds starts to come into play. And finally, magnetic hard drives are still a thing. This used to be the dominant form of non-volatile storage. Very quickly now, solid-state drives are overtaking them, but they still have a purpose. They still are very cheap, so about a third of the price of solid-state drives, at least, as of right now when I'm recording this video. And but latency is pretty bad on solid-state drives, and so latency is determined by literally the physical spin rate of the magnetic platters within the hard drive, and maximum data transfer tends to be on the order of 600 megabytes per second, so several times slower than flash. And so because of flash's speed, you see it a lot in gaming computers now, and solid-state drives are really starting to overtake magnetic hard drives. Okay, so now most computers have at least three different types of memory in them. There's some sort of non-volatile storage. Let's say it's flash storage. There is some super fast but relatively small and expensive SRAM. And then kind of in the middle, in terms of size and performance, we have our DRAM. So we have three different types of memory that each have different trade-offs in terms of size and speed. And this means we have a memory hierarchy within our computer. And to understand how we manage this memory hierarchy, it's worthwhile thinking about retrieving information from a library. And so this analogy is for back when we used to go into libraries to read books. That's still kind of a thing, although I'm recording this during COVID, so nobody's really physically going into libraries right now. But let's imagine we have a world where that is still possible. And let's assume we have a library with basically two tiers of information access, or two ways to access information. When you go into the library, one thing you can do is retrieve a book from the shelf. And that refers to going to the shelves, finding a book you're interested in, and then coming back to your cubicle. The second tier of information access is then just reading that book. So once you have the book, you're able to open up the book and page through it and read whatever information that you want. And so what we're going to do now is we're going to consider two scenarios that will give us some insight into how we want to manage memory and information flow within a computer. Okay, so let's assume that you're interested in doing some web development and you're thinking about using Python as your programming language of choice. And so in scenario one, we have a whole sequence of events. The first thing we do is we go to the shelf and find a book on using Python to write web apps. And we bring the book back to the cubicle that you're using in the library. You open up the book, you read about some basic syntax, then you close the book, you return the book to the shelf, then you come back to your cubicle, and then you think about what you've read. And then after thinking about it, you're like, I should probably find out about how secure Python is, or the security capabilities of programming in Python. And so you go back to the shelf, grab your Python book, bring it back to the cubicle, read about security, and then once you're done reading about security, you go all the way back to the shelf and you return the book to the shelf. Then you return to the cubicle. And you sit there and you think for a little bit and you're like, I might want to develop maybe in Ruby. I'm gonna also look into Ruby as a language. And so you go to the shelf and you find a book on Ruby, you bring it back to the cubicle, you read a little bit about Ruby, and so on. And so basically in this first scenario, you're constantly running back and forth to the bookshelf. You run to the bookshelf, you bring a book back, you open it up, you read a little bit, you close it, you put it back in the shelf, then you come back to your cubicle, you sit there and read, and then if you want more information, then you go back to the shelf. Obviously, this is inefficient. Scenario 2 is a scenario that's a lot more efficient and has you spending a lot less time running back and forth between your cubicle and the shelves. So in scenario 2, you go to the shelf and you don't just choose one book on Python, you grab a few of them. And while you're there, you look at the other books that are on the shelves, and it's the web programming section, and you see, oh, okay, there's a Ruby book, so maybe I'm going to grab that. I might grab a book on PHP as well. And you take a stack of books and you bring them back to your cubicle. It still takes the same amount of time to get to the shelf and get back, but you're bringing a lot more information with you. You then bring the books to the cubicle and you keep them in the cubicle while you're doing your work. So you read about Python syntax, you think about it, you keep your books right with you. Then you open up the book again and you read about security. Then you do a little bit more thinking. Then you open up the books on Ruby and PHP and you read those. Then you do a bit more thinking. And then once you're done processing all that information, that's when you return all the books to the shelf. So rather than running back and forth to the bookshelf every time you want a new little piece of information, you grab a whole bunch of related information all at once, you bring it back to your cubicle, and then you read through the books while you have them with you. And so the scenario 2 takes advantage of two concepts. The first one we refer to as temporal locality. And that refers to the notion that if you've used a piece of information recently, you'll likely need it again soon. And this is the Python book in our example. So we've used the Python book, we read something in it, then we set it aside, and then we bring that same piece of information back and we look at it again. And so that's temporal locality. The other type of, or the other concept that scenario 2 takes advantage of is something known as spatial locality. And spatial locality refers to the notion that if you use one piece of information, the other information that's in the same area may be useful to you as well. And that's the idea of going to the bookshelf, grabbing a couple books on Python, but then also seeing that there's books on Ruby and PHP as well, which is related, and you grab those as well, just in case you might need them. And the notions of temporal locality and spatial locality really will govern how we manage information flow between the different tiers of memory that we have in a computer. Okay, and so now how do we extend this library discussion to computers? So as I mentioned, most modern computers have at least 3 levels of memory in kind of a memory hierarchy. We have some sort of non-volatile storage. Let's say this is a flash solid-state drive. We have some DRAM main memory, and then typically we have some SRAM built literally right into our processor chip. So this would be inside the ARM chip, or the typically you don't see cache memory in little 8-bit microcontrollers, but in Intel chips, ARM chips, stuff like that, you'll definitely always see cache there. And we know that these 3 levels of memory make different trade-offs in terms of size and speed. Non-volatile storage is big and slow. SRAM is small and fast, and DRAM is in the middle. And you can think of going to non-volatile storage as walking all the way to the bookshelf and grabbing a book. It takes a long time. And you can think of having information in your SRAM cache as having a book right in your cubicle where you can access it really, really quickly. And then, again, DRAM is somewhere in the middle. The notions of temporal and spatial locality exist in computer programs just like they do in libraries. And so temporal locality refers to the fact that if we are working with a variable in memory and we've used it once, chances are the program is going to use it again relatively soon. The notion of spatial locality typically occurs when we're working with arrays. So if we're working with one value in an array, chances are we're going to want to do some kind of operation with its neighbors as well. And these notions of temporal and spatial locality have been verified by software engineers that have studied memory accesses. And so our design objective then is to use the notion of temporal and spatial locality to basically try and anticipate or guess what data that our processor is going to want to work with, and to prefetch it and put it into high-speed memory. So we want to take a bunch of stuff from low-speed memory, put it into high-speed memory, where the processor will then use it. Just like in our library example, where we grabbed a whole bunch of books off the shelf, we maybe weren't sure for sure if we were going to use all of those books, but we had a pretty good idea that we would, and we brought them back to our cubicle, and sure enough, they came in handy. So in our examples in this lecture, we're going to be working with the ARM microarchitecture. And the reason why we're sort of leaving the AVR behind at this point is because AVR devices are too simple to have caches. And also, ARMs work with, typically 32-bit or 64-bit words. And that's, it's important to have experience working with longer words when doing cache examples as well. So we're going to, in this lecture, assume a 32-bit ARM microarchitecture. And there's a lot of different versions of ARM out there. So, but the one that we're going to assume uses 32-bit words and 32-bit byte level addressing. Sorry, I should have added that in. Byte level addressing with little endian, with the little endian convention. And just as a bit of background for our microarchitecture, so the ARM, just like the AVR, the ARMs do have register files that contain a bunch of general purpose registers. We're going to assume an ARM architecture with 16 32-bit registers. Registers 0 through 3 are used for temporary values and procedure calls. 4 through 12 are general purpose registers. Just for information, register 13 is our stack pointer. 14 is used for branch instructions, and 15 is the program counter. We're not going to use any of these special purpose registers. We're just going to use the general purpose ones. But this is just to sort of put things into context relative to what we've been talking about in the previous lectures with AVR. And there's two ARM assembly language commands that we're going to be using in our examples. LDR and STR, or load register and store register. Sometimes I'll refer to these as load word and store word commands, because we're dealing with a full 32-bit word. These are analogous to the LD and ST commands that we've learned for the AVR. And they have kind of a similar format, I guess. So LDR, the format of the LDR assembly language command is LDR, the register we want to load our value into, and then we specify the address, the data memory address that we're trying to read from. And the command gives us sort of two ways to specify the address. We can provide a register that contains our 32-bit address. And this is similar to the XYZ register pairs that we learned about for the AVR. But in addition, something that's a little bit new is ARM assembly also allows us to specify an offset that's encoded as an immediate inside the machine language instruction itself. And the offset is, the size of the offset varies depending on the type of assembly language and architecture that we're assuming for ARM, but we're going to assume a 17-bit offset that is stored, again, in the command as an immediate. And so for basically all the examples in this lecture, we're going to see things like LDR, I'm going to give some register, maybe R5, and then in all cases, I'm going to give register 0 as the register containing our address, and then I'll give some offset. In all of the examples in this lecture, I'm going to assume that the register R0 contains 0. And the reason why I'm doing that is just for readability. So basically what that means is that the actual address we read from is calculated as R0 plus the offset. And if R0 is equal to 0, then this offset is basically the address that we're going to read from. And the reason why I'm doing that is just so things are a little bit more readable. So R0 is 0, and so then this is basically just our address. I should also mention that this lecture, I used to teach MIPS assembly language for this lecture. I've modified this video to now conform to ARM, and in some ways I've taken sort of MIPS slides and I've overlaid ARM assembly language instructions on it. I think everything kind of hangs together. But sometimes you might hear me possibly refer to MIPS still at various points in the lectures, but basically just assume that we're working with ARM at this point. The store word command, str command, works in basically exactly the same way. So store word, the format is str, and then you give the register that you want to write to data memory, again, R5, R6, whatever it is. Then the address that we want to write to is equal to our register rn plus our offset. I'm always going to give register R0 as our register. Again, we will always assume that that register contains 0. And then I'll give some kind of 17-byte, 17-bit offset value. And so these are the two commands that we're going to see as we work through these examples. Okay, so now let's go over a little bit of caching terminology. First of all, when a hit occurs when a desired memory word is contained in the cache. So when we want a certain memory address and we go into the cache and we look for it and it happens to be there. So we've anticipated the needs of the processor. A miss occurs when the processor looks in the cache for a particular memory word and it's not there. The capacity of a cache is just the number of memory words that can be stored in the cache. In these lectures, we'll be looking at 32-bit words. So the capacity is a certain number of 32-bit words. The term block refers to the number of adjacent words that are fetched when a single word is loaded into cache. And this is how caches take advantage of spatial locality. So we mentioned that, if we need one piece of information, then chances are we need the other pieces of information that are close by. And that's why when we want to when we ask to load a single word into the cache, typically we don't just load that one word, we load a block of words that are located around the word that we've loaded, and that's what block size or that's what a block refers to. The size of the block is just the number of words in the block, as you would imagine, and just a few variables here. If C is the cache capacity and little b is the block size, then the total number of blocks in the cache, of course, is just C divided by B. And one last little bit of terminology, we also refer to cache sets. And so we're basically going to take the whole cache and we're going to divide it into a bunch of pieces or sections, and each section is going to be referred to as a set. And this is how we are going to represent caches. There are a whole bunch of different caching styles and caching strategies, and we're just going to talk about the basics in this lecture. And so we're going to be working with something that's known as a direct mapped cache. And this is just a terminology to remember. We're not going to look at any other types of caches, but just remember this one, because if you take an advanced course on computer architecture, you'll probably look at a bunch of different strategies. So a direct map cache is where the set size equals the block size. And so we're going to divide our cache into a bunch of pieces, and the size of each piece is going to be equal to the block size. And so here's a couple examples of a couple different simple cache organizations, and how we're going to be drawing them when I work through these lectures. This first cache has a total capacity of 8 words. Very small. Most caches have way more than this, usually kilobytes of capacity. But just to keep our examples simple, we're going to be looking at very small caches. So our total cache capacity is 8 words. Our block size is just 1 word, so we only fetch 1 word at a time. And that means the number of sets that we have is equal to 8. And so the first word in our cache also corresponds to 1 block and also corresponds to a set. The second word is a set the third word is a set, and so on. So we have a total of 8 sets. Now, the second example also has a total cache capacity of 8 words. However, our block size is equal to 2 words now, so we reread 2 words at a time from main memory and when we put data into the cache. And that means our total number of sets is equal to 4. And so these 2 words are a set. These 2 words are a set, and so on. So we have a total of 4 sets in this particular cache. And this is going to make more sense as we work through some more examples of how data is actually loaded into these memory areas. So for the first part of this lecture, we're going to be focusing on what happens in the cache when we load values from memory. So basically when we execute a load word style assembly language instruction. So we're for now just going to talk about reading things from memory and how, when we perform a read, how data is transferred from main memory into the cache. A little bit later on in the lecture, we'll talk about writing things to the cache and how that's then transferred back into main memory. Caches are always smaller than main memory because SRAM is more expensive than DRAM, so we always have a smaller amount of it. But we still want to be able to map our entire main memory address space to our cache. And that just means that we're going to have a bunch of main memory addresses or main memory words that map to the same location in cache. And so here's an example where we have a 32-bit address space in main memory, and we have our one word cache with a capacity of 8 words. And as we said in the previous slide, this means that we have 7 sets, or we divide our cache into 7 sections, basically. The first address maps to the first set, or the first location in cache. Our second 32-bit address maps to the second location, and so on. So the first 8 words in main memory map into the first 8 locations in the cache, which, I hopefully makes a little bit of sense. And then basically what happens is we just wrap around. So once we reach the end of our cache, the next location in main memory then just maps back to the first cache position. The second maps back to the second cache position, and so on. So relatively straightforward mapping. It gets a little more complicated when we have a block size of greater than 1, but still not too bad. So this is an example where we have our 8-word cache, but we have block sizes of 2. And so that means we only have 4 sets. And the first 2 words are mapped into the first set. The second group of 2 words are mapped into the second set, all the way up. Addresses 8 and 9 are then mapped back to the first set. So again, we have this sort of wrapping around, except we have 2 words mapped to the set. And specifically, I sort of drew these arrows as both words going to the same set, which is true. But really what happens is this first word is mapped here, and this second word is mapped here. This first word would be mapped here, and this second word would be mapped here. And you can imagine how this would grow if little b was equal to 4 words, or if our block size was 4 words, we would just have a row of 4 words all side by side in our cache, and the first set would consist of 4 consecutive words. So if it's possible to map multiple main memory locations into the same cache location, we need some way to figure out which main memory word we actually have stored in our cache at a particular time. And that's what we use something called the tag bits for. So the tag bits identify which main memory location is currently stored in our cache. And we literally store those tag bits right beside the cache entry. The set bits are the bits that identify which set we need to copy our word into, and that's basically the set bits determine those arrows that I showed you in the previous slide. And both the tag bits and the set bits are extracted from the main memory address in kind of an intuitive way, and I'll show you an example of how that works. The last thing we're going to store in our cache is something that's called a valid bit. So a valid bit is equal to 1 if the cache block holds valid data. And so you can imagine that if we reset our processor and the processor first starts up, there's been no load word commands executed, so we haven't read anything, we haven't tried to read anything into the cache. So the cache is basically empty, and so all of our valid bits would be equal to 0. However, as we load main memory words into a particular cache location, we always set the valid bit at that point equal to 1. So in the next several slides, we're going to work through a single word cache example where we have one word block sizes, a cache capacity of 8, and we're going to assume 32-bit ARM addressing. So 32-bit addressing where our addressing is byte level and Little Endian. And this slide basically shows how we're going to take our main memory address that our LDR or STR, or load word and store word assembly language commands use, and figure out what region of the cache we need to map those addresses to. And so since we're using byte level addressing, we know that our addresses go up in increments of 4. And so our byte offset is basically the first 2 bits of our address. And these are essentially unused. We have a cache capacity of 8, and so we basically need to use the next 3 bits to figure out where we map into our cache, what set we map into our cache. And so in our previous example, when we were mapping words into sets, and we were in the first set, second set, third set, and then we wrapped around, that's basically what we use these 3 bits for. And then essentially what we use the remaining, 27 bits for is these are our tag bits. In this next slide, this is basically sort of the logic design of our cache. And so we have 8 sets, as I mentioned. We need 3 set bits to indicate which set we're mapping into. We have 32 bits to store our data word that we're pulling in from main memory. We have 27 bits to store the tag for each cache entry, and then we have a valid bit. And these valid bits would all be 0 to start with, and then we change them to 1 when we write in a word. And so up here, this is showing how we take the main memory address that's being used by our load word command, and we break it into sections in order to access our cache. And so like I said, we get rid of the bottom 2 bits. I'll just clean this up. We use the next 3 bits to index which set, so we sort of go up and down and we select our set based on these set bits. And then the last 27 of our tag bits, are copied into our location. And so if we're reading from, when we're reading from our cache and we want to determine whether we've got a hit or not, we take the 27 bits from our main memory address that we're working with. We determine which set our word should be in, and then we pull the tag bits from whichever tag bits happen to be there, and we compare them. So we compare the 27 most significant bits of our current address with the 27 tag bits that are stored in our cache location. If they're the same, that means that this word already exists in cache and we potentially have a hit. If they're not the same, then we have a miss. And so the output of this equality test will either be 1 or 0. And then the last thing we have to do is also test if our cache entry is valid. And so if it's valid, then this line is going to be equal to 1. If the 27 most significant bits in our load word address map the 27 most significant, or map the tag bits stored next to our cache location, then this is going to be 1 as well, and then we get a hit. If our tag bits don't match the 27 most significant bits in our load word address, or if our valid bit is 0, then we get a miss. And then regardless, the data word is going to be, the cache data word is going to be output on this 32-bit data bus. However, if hit is equal to 0, then we would just ignore the information on that bus. We would only use it if hit was equal to 1. Okay, so now let's work through the next part of our example. Now there's a ton going on this slide, and I'm going to go through it fairly slowly. But again, this is probably one of those places in the video where it makes sense to kind of pause, think about what I'm saying, look at your printout of this slide, and make sure you sort of understand everything that's on the slide. And so big picture, we've kind of got, I guess, 4 important regions on this slide. This area of the slide shows a section of main memory. So we have a 32-bit address space. We have the addresses 048C, and then we take a little jump up to 83C, 8040, 8044, and 8048. I jump up in address just to sort of show what happens when we use a different range of addresses with our cache. Over here we have our 32-bit word values, 112233, and they just go up from there. In this section of the slide, I've got a picture of our cache. And so this is, again, an 8-word cache with 1-word block sizes. And so we've got 32 bits to store our data. We've got 27 bits to store our tag, and then we have 1 bit to indicate whether or not our cache entry is valid. And what we're going to do is we're going to sort of look at how the contents of our cache changes as we execute a series of load word assembly language instructions. And so this is the assembly language instruction that we're executing. And then this part of the slide helps us sort of break out the binary version of our address and then extract our set bits and our tag bits. Okay, and so these are the big regions of the slide. So let me just kind of clean things up a little bit here. Okay, so the first thing we need to figure out is what main memory address are we accessing. And so for our load word command, we've got a base address of 0 and an offset of 4. And so this is the main memory, the location in main memory that we are loading with our load word command. This is the main memory address. And what I've done is I've broken it out in binary form. Okay, so we know that these bottom 2 bits are the byte offset. We throw those away. We know that the next 3 bits are our set bits, and then the remainder of this corresponds to our tag. The 27 bits correspond to our tag. And so that means our set bits correspond to 001, or in hex, this would just be 1. Our tag bits are all 0, and I've kind of broken, I've moved the just as to sort of clarify my notation here, I've taken these 27 bits and I've just moved them down here, but I've changed the little underscore separator. So these 8 bits correspond to these 3 bits plus those 5 bits. The next group of 8 bits correspond to 3 bits and 5 bits and so on. The reason why I did that is just a little easier to translate our tag bits into hex if we have that kind of separation. So again, just to clean things up here. So our tag bits in this case are all 0. And so what happens down in our cache, we access set number 1. So this is where we're going to be writing our data bits. We copy in the memory location or the value 22 into our data section. Our tag bits are all 0. And we now have, we set our valid bit equal to 1 for this particular entry. This would be considered a miss, a cache miss. We went to load the cache, it wasn't there, and so then we had to copy in the location. In fact, all of the load word commands we're going to go through in this first example are going to be misses. Okay, in this next example, we have a load word command where, again, we have a base address of 0 and an offset of 8. And so that means that we are accessing this area of main memory. If we take our word address and we break it out in binary form, these lower 2 bits we get rid of because they're the byte offsets. Our set bits are the next 3 bits, which correspond to 0, 1, 0. So that means we're going to copy our word into set 2 in the cache. And our tag bits are the upper 27 bits, all 0 in this case. And so the new entry in our cache corresponds to data value of 33, because that's what was located at address 8. Our tag bits are all 0, and our valid bit now is equal to 1. In the next slide, we have another load word command where, again, our base address is 0 and our offset is 83C. And this corresponds to, this location in main memory. And so this is our 32-bit address. Our address now is a little bit more interesting. We have a few more 1s in it, I guess. And so we get rid of our byte offset. We take the next 3 bits to determine our set number. Our set bits are equal to 7, so we're actually loading into set 7 now. And these 27 bits, when you express them in hex, are 0000401. So it's hex 401. And so the data value we load into the data section of the cache is 55, because that's what's stored here. Our tag bits now are equal to hex 401, and our valid bit is equal to 1. So you can see we're starting to fill in our cache a little bit now. The next address that we load in is 8048. And if we specify the binary version of this address, getting rid of our bottom 2 bits, our set bits are equal to 2. And that means that we're going to copy into, we're going to check set 2. And this area of the cache already contained some data from an earlier load word, but we just overwrite the data. So what happens is this load word command will check this area of the cache. It'll see that the valid bit is equal to 1, and then it will compare its tag bits, right? So if I can just sort of draw this here. Before, the tag bits used to be all 0s, and the data value was 33. And so when the load word command tries to load a word from address 8048, it's always going to check to see if this value is already in the cache first, right? And the way it does that is it determines the tag bits in the address that it wants. In this case, the tag bits are hex 402, and it will check the tag bits already in set 2 to see if there's a hit. The problem is, though, that the tag bits currently stored in set 2 are all zeros, and so that little logic circuit that I showed you a few slides ago that compares the tag bits on an incoming address and the tag and the word already stored in cache, that's going to give us a 0. And so this is going to be a miss, and then what happens is we load our new tag bits and our new value into the cache. The reason why we do this is temporal locality. So we assume that the data, because we're accessing the data at address 8048 more recently, we assume that it's more relevant than the old data that's already stored in the cache, and so we just replace the old stuff. So the cache will always overwrite old data. And so then what happens is we overwrite the value in set 2 with the memory value at location 8048, and we overwrite with the tag bits that correspond to 8048. And then the last example is 8044. That's this location. When we look at the binary version of our address, we see that our set bits are equal to 1. That that set already contains data from the very first load word command that we issued. And so again, what's going to happen is the computer will determine the tag bits for this current word that we want. Our tag bits here are hex 402. And it's going to check the tag bits that are already in the cache. However, for our previous entry, the tag bits were all 0. We don't get a match, and it's a miss. And so then what happens, because the data that was already in the cache is older, we overwrite the data. And so we take the data memory value 77 and our new tag bits, hex 402, and we put those in the cache. And so hopefully what these examples will show is how data sort of flows into the cache when we execute different load words, how it gets mapped to different regions of the cache, and what happens when we get a miss, right? So we just basically overwrite the data. If we happen to get a hit, we're not showing a hit now, we'll show a hit later on. If we happen to get a hit, then really nothing in the picture changes, right? So we look to the cache, the data that we want is already in there, and so we pull it out of the cache, and then nothing within the cache would change. We just read that data out. Okay, in this next example, we're going to again work with 32-bit ARM addressing. Our cache capacity is going to be equal to 8, but we're going to work with 2-word block sizes now. So that means we're going to have 4 sets, and each set is going to contain 2 words. So this slide shows how we're going to use our main memory address to figure out our tag set and now our block offset bits as well, because we have a block size of greater than 1. So just like before, the lower 2 bits are our byte offset, which we can basically discard. Our block offset, because we've got 2 words in each block, we just need a single bit for block offset. So we use our 3rd bit, which has a bit index of 2. That doesn't mean there's 2 bits here. That's just our block offset is the 3rd bit, which has a bit index of 2. Because we've only got 4 sets now, we only need 2 bits. So the next 2 bits are our set bits, and then the remaining bits are what we use for our tag bits. The logic circuit that we would use to implement this cache looks something like this. So kind of related, but you can see we've changed things a little bit. So we still have a valid bit. We still have 27 bits for our tag. We still determine a hit by comparing the 27 bits of our incoming address with the 27 tag bits that are stored in our cache. We index our set using the set bits, except now we only have 2 because we only have 4 sets to choose from. I should remove these. So we don't have 3 bits, we only have 2. And within, so then each cache entry consists of 2 words. And when we want to read out our 32-bit word from the cache, we need to figure out which one of these 2 words that we select. And we do that using a multiplexer and the block offset bit. So we pull the block offset bit. If the block offset bit is equal to 0, then we pull this first word out of our block. If the block offset bit is equal to 1, then we pull this second word out of the block. So the mechanism for determining whether or not we've got a hit is exactly the same, except now we've got 2 words in each cache set, and so we need to be able to pull out 1 word from within that set. And we're going to move on and extend our another example where we have a bunch of load word commands and we populate our cache, and this will become a little bit more clear as we work through that example. Okay, so in this example, our slide organization is exactly the same as before. This is main memory. This shows the contents of our cache. It's a little bit different now because we have a 2-word block in each cache entry. This is the load word command that we're going to be executing, and then this part of the slide helps us to determine our tag bits, set bits, and also, brand new for this example, our block offset bit. So let me clean this up, and we'll take a look at what we've got going on. So this first load word command is exactly the same as the first load word command in our previous example. So we want to load the value at address 4. And if we break apart our binary word address, or if we break apart our word address into binary, our first 2 bits are the byte offset. We get rid of those. The next bit is our block offset. And then the 2 bits that follow are our set bits. And so our set bits are 0, 0, and our block offset is 1. That means that we're going to store our result in the first set. The actual word that we're storing, because our block offset is equal to 1, this is the word that we fetched. However, whenever a cache goes in to store 1 word, it brings along all of the other words that happen to be in the same block. And again, the reason why we do this is to take advantage of spatial locality, the idea that if we need 1 word, we might need the data that's close to it. And it also helps us improve our memory transfer rates. So we saw right at the start of the lecture that RAM, flash, can go faster if we are fetching words at consecutive addresses. And that's exactly what we're doing here. So even though we're fetching this word, we're going to bring along this one as well because it's in the same block, right? So that's why this word is 0, 1, 1. And pulling 2 words together is faster than just fetching 1 and then fetching another word from a different address. Now, in a real cache, these block sizes are much bigger. So we're pulling in, literally hundreds of words at a time. And so we see a speed improvement, or maybe even sometimes thousands of words. Our next load word command wants to load the word at address 8. If we break apart the binary address, this is our byte offset. The next bit is our block offset. And then the remaining 2 bits are the set bits. So we're loading into set 1. Our block offset is 0, which means the word that we were trying to load with our load word command is here. But again, we're going to bring everything else that's in the block that contains the word that we want. And so in this case, that means we bring along the value 44 because that's the next word in the block. And so you can see, like, if you look at how main memory is divided, the first 2 words are in a block, the second 2 words are in a block, and then if you take either of those 2 words, both are going to be loaded into the cache. If you take either of these 2 words, again, both are going to be loaded into the cache. The next example is when we're going to, in this next statement, we're going to overwrite a cache entry. So we're now looking for the word at address 8040. And so if we break this, or if we express this as binary and we break it into pieces, this is the byte offset. Our block offset bit is 0. Our set bits are 0. And this puts us back into the first set. We're going to check to see if our tag bits match, but they won't. So originally, on the previous slide, these tag bits were all 0. So we're going to check to see if the tag bits of our current desired address match. They don't. Then it's a miss. And so then what's going to happen is we're going to overwrite our contents. Because our block offset is 0, this is the value that we were trying to fetch, but we're going to load in the value that was in the same block as our desired word, which corresponds to 77. Now, finally, after all of these misses, we're actually going to get a hit. And so we're now trying to load in the word at address 8044. We haven't tried to load this word yet, but when we look at the binary version of the address, this should be 8044. We have we get rid of our 2 byte offset bits. Our block offset is equal to 1. Our set bits are equal to 0. And so we know where we need to check this particular set. Our tag bits, these 27 tag bits, correspond to hex 402. We check the tag bits in set 0 and they match. Amazing. So we now know that the block that we're looking for is already stored in the cache, and because our block offset is equal to 1, this is the value that we fetch. So we're able to fetch the value 77 from high-speed SRAM cache rather than having to go all the way back to main memory and use a slower DRAM fetch. So anyway, that's at least one hit, so that's good. And it shows the value of spatial locality, right? We didn't originally specifically fetch the address at 8044, but when we fetched the address at 8040, we thought, you know what? These values are right beside each other. Spatial locality tells us that maybe the program's going to want to have the next address, so we're just going to pull it in anyway. And sure enough, in this case, it paid off for us. Okay, so up until now, like all of our cache examples have been talking about loading, load word commands, like basically reading or loading values from memory. Now it's important to also talk about how caches work when we're trying to write or store values in memory. And when performing a store word type command, the processor will determine the tag bits from the address that is contained in our store word command, and will check the cache to see if those values have been loaded into the cache. So it's exactly like checking for a hit with a read. We compare the tag bits stored in the cache with the tag bits in the address in our store word. If they match, that's a hit, and we write our value directly into the cache. If it doesn't match, then it's a miss. And then actually what we do is we go to the cache, we copy in the values in our desired block into the cache, and then we change the value into the cache. And so, again, for a hit, we write directly to the cache. For a miss, we read the desired values into the cache, just like we did with load word, and then we modify the value within the cache for doing our store word. And now when a value is modified within the cache, there are two sort of strategies that are used to then kind of copy that changed value back into main memory. The first one is write through, which is a very simple strategy, and it basically says anytime a value in cache is written, write the same value into main memory immediately. So it's not super efficient because you're constantly writing to main memory. Every time you update something in cache, you update the same thing in main memory. The second strategy, which is a little bit more efficient, is something called write back. And write back requires us to add another bit to our cache entry that's known or referred to as a dirty bit. And the dirty bit is stored right beside the valid bit. And it basically records when a write has been performed on a cache block. And so if we write to a cache entry using store word, the dirty bit is set equal to 1. And that's how we know that a value has been changed within the cache, but has not yet been changed in main memory. And so when the time comes to overwrite that cache block and replace it with newer data, we'll check the dirty bit and say, oh, we've got a changed value here. We then change that value in main memory and update the cache. And we'll do an example to sort of show how this all happens. Okay, so here's a more abbreviated example where we have a series of load word and store word commands. And we're accessing a series of memories or memory locations. And, at the bottom here, I'm just, for the first line in the assembly language program corresponds to the notes connected to the number 1 here. What happens from the second assembly language command corresponds to the notes on number 2 down here, and so on. I also copied in a little diagram of the cache we're working with. So we're working with an 8-word cache with 2 word block sizes. You can just draw this in if you want. And let's get started. So the load word command wants to access a memory offset set of 8. And I'm not going to show the full binary detail of the address. I mean, we've already worked through that. But just to summarize, this address corresponds to the set bits 0, 1, and a block offset of 0. And so that means that we are writing a word in here. This is the exact word that corresponds to our what we're addressing with our load word command. And then we load something into here as well, because that happens to be the other word that is contained in our block. And so we load the memory values at address 8 and address C. Then in our next instruction, we want to write a value to main memory address C. We check our cache, first of all, and we determine that this corresponds to set 1, a block offset of 1. So that's this memory location. We check our tag bits and our valid bit, and we figure out, hey, this update or this memory location is current. So I'm just going to write directly to this cache location. We're also going to have, just drawing it off to the side, a dirty bit, and we would set the dirty bit equal to 1 because we have written to this cache location. So now the value in the cache no longer matches the value in main memory. This would be considered a write hit because we are writing to a location in the cache that contains a valid address. If we were implementing the write through policy of main memory updating, then basically as soon as we write to this cache location, we would also update the value in main memory. If we were implementing the write back strategy, we would set the dirty bit equal to 1, but we wouldn't yet write back to main memory because nothing has tried to overwrite this location in the cache yet. That's going to happen though. Okay, let's go on to line 3 now. So in line 3, we want to store the value in register T1 in memory location 0. This corresponds to set 0, block offset 0. So it's this memory location. And if we were to check our valid bits, so this is a V, the valid bit here would be a 1 because we've been working with this area, but nothing yet has been written here. And so there's not a valid cache entry in set 0. And this would be considered a write miss. And so the way the cache works is it doesn't just sort of write to this memory location and then say, okay, well, that's fine. What we do first is we load the values from main memory and then we change them. And so on a write miss, what we do is we load the values from address 0 and address 4. So both of these locations have valid data. We then change the value at that particular cache location. And you could say, well, you've just read something and then overwritten it. Isn't that inefficient? And it's true. You could imagine more efficient ways to do this. But for conceptual purposes, let's just assume that we read it in and then we change the value we want to change. Okay, so now after our load and our write, just get rid of this. Our valid bit is going to be equal to 1. And if we were using the write back, our dirty bit would be equal to 1. And so the next thing we're going to do is we're going to execute this load word command. And it's going to try to load a value from address 8040. And the set bits and block bits for address 8040, or the set bits correspond to this first set. And we've already got data in here that we have modified because our dirty bit is equal to 1. Now, our processor is going to check the tag bits on address 8040, and they're going to find that they don't match the current tag bits in set 0. And so what's going to happen is we're going to overwrite this data. But before we do that, the processor is going to take note of the fact that the dirty bit is equal to 1. So before we overwrite the set 0 with the values at address 8040, we're actually going to do a write back. And so we would do a write back, copy in the new value into data memory, and then we would load in the values at address 8040 and 8044. Interestingly, this is one, we sort of think of the write through, write back strategy as being really, really wasteful, like always writing over and over and over again. However, this is one case where the write through strategy would not perform a write, because it did its write in the previous command. And so it's already taken care of copying the updated value back into main memory. And so when the values in set 0 are replaced, with a load word command, we don't have to worry about writing them back. So it's a little bit less complicated in that way. Okay, so our final command, this last store word command, is going to cause a whole bunch of things to happen. So this last store word command wants to take the value in register T4 and copy it into address at 8048. Address 8048 corresponds to set 1, block off set 0. And if we look at set 1, it already contains data that was loaded in back with this store word command. And so the tag bits are going to be all 0 from this previous command. And so the store word on line number 5 is not going to, it's going to record a miss, and it's going to say, okay, I need to update this, this cache entry, and then I'm going to change it. However, we already have an updated value and a dirty bit equal to 1. So what's actually going to happen is, first of all, the write back is going to be triggered because the dirty bit is equal to 1. And we're going to copy the value back into main memory that was written up here by this first store word. We're then going to load in the memory values at 8048 and 84C, right? And so these two locations are going to be reloaded. We're then going to change this location, and we're going to set the dirty bit excuse me, back to 1 because we now have an updated value thanks to this the store word command on line 5. And so lots going on here. So in this example, I've compressed it so I can show everything on just one slide. However, there's a bunch of steps going on here. And so you might want to choose to create different diagrams for yourself that show things step by step, or write things down, step 1, step 2, step 3. But just know that we've got, like, for each one of these assembly language functions, as we've discussed, there's a bunch of stuff going on in the cache. Sometimes we do a write to a cache location. Sometimes we read something in and then modify it. Sometimes we copy something out, read something in, and then modify it. So there's a lot going on. So take your time working through this example and definitely watch it again to make sure things are solid. Okay, so it's worthwhile to also say a few words about how we measure or evaluate cache performance. So in general, we know that cache hits are good, right? Like when we go to fetch a value from memory and we find it in the cache, we can do a quick SRAM memory access rather than having to go all the way out to slower DRAM main memory to get the value that we're interested in. And so one of the metrics we use is hit rate and miss rate, and the definitions are very straightforward. So hit rate is the number of cache hits divided by the total number of times we try to access memory. Miss rate, the number of misses divided by total access. Hit rate is 1 minus miss rate. And of course, we want hit rate to be as high as possible. We'll never get 100%, but we want to make it as high as we can. We can also determine the average length of time it takes us to do memory access. So every memory access, our memory accesses throughout the execution of our program are going to be a mixture of cache accesses and main memory accesses. So we'll access from cache when we get a hit, main memory when we get a miss. And so the average length of time it takes to do a memory access is our hit rate multiplied by the length of time it takes to access our cache, plus our miss rate multiplied by the length of time it takes us to access main memory. And in this class, we'll measure these times in terms of cycles, clock cycles. And we know from the start of the lecture that an SRAM access, we can say it takes approximately 1 clock cycle to complete, and then a DRAM access would take perhaps 100 cycles. And so let's just do a quick example here. In this example, we've got 4 load word commands for a series of addresses. In this case, we have a 16-word cache and 4 word blocks. So that means we have 4 sets, each consisting of 4 words. So we're going to have 2 set bits and 2 block bits. I'm not going to bother showing the entire 32-bit binary address. I'm just going to show the first 8 bits. So address 44 corresponds to, if we get rid of these as our byte offsets, these are our block bits. These are our set bits. And these are our tag bits, assuming an 8-bit addressing scheme. And so our first load word command corresponds to tag bits of 0, 1, set bits of 0, 0, and block bits of 0, 1. And our cache is completely empty at this point. We're going to assume that we're starting from scratch, basically. And so the very first time we load in a word, we're going to get a miss. The second time, we are looking for address 4C. This corresponds to tag bits of 0, 1, set bits of 0, 0, and block bits of 1, 1. Because the tag bits that we're looking for now match the tag bits that would have been copied into the cache after our first miss, this is a hit. We then load in address 48. Again, our tag bits are the same. And so this means this is going to be a hit. You know, we've determined the set bits and block bits as well. You can see that, you know, we're accessing different blocks within the cache. But basically, as long as our tag bits match, and as long as we have a valid entry in the cache, it's a hit. And so our second load is a hit. Our third load is a hit. And then finally, we load address C8. Here, our tag bits have changed. And so that means that we have a miss in the last. And so our hit rate, you know, very simply, we've had 4 memory accesses. 2 of them were hits. So our hit rate is 50%. And then our average memory access time is 50.5 cycles. And so this kind of, I guess, to kind of conclude this discussion, this really highlights one of the characteristics of caches. So main memory is takes 100 cycles. The cache only takes 1 cycle. And, you know, a hit rate of 50%, yeah, it cut our memory access in half. We went from, you know, theoretically a worst case of 100 down to 50, but we're still pretty far away from that 1 cycle time that we would get if we ideally had a 100% hit rate. And so this really shows that we need to design our caches to try and get a much better hit rate than just 50%.